you very much, Andrei, for introducing me, and I would like to thank the organizers of the conference for giving me an opportunity to give a talk on this conference. So, and the title of my talk is Hybrid Helical State and Superconducting Diode Effect in Superconductor Ferromagnet Topological Insulator Heterostructures. So actually my affiliation is HSE University, which is a rather young university in Russia, and Lebedev Physical Institute, actually where I'm working in the group of Professor Zaikin. Let's start with helical state. So helical state, actually this is a rather new field. So what is a helical state? It's developed usually in 2D superconductors, and two important ingredients are needed. So it's a breaking of time reversal symmetry. For example, it can be in-plane magnetic field, but as well it can be exchange magnetic field. It means it can occur in SF hybrid structures and so on. And another important ingredient is breaking inversion symmetry. For example, spin-orbit coupling, but there can be other more exotic variants like asymmetry of the junction and so on. So in our case, it will be spin-orbit coupling. And I would like to explain how the helical state is introduced. So usually if you have spin-orbit coupling, you have this kind of term in the Hamiltonian, where sigma is a Pauli matrix vector, so it's spin matrices, P is the momentum of the electron, and N is a vector normal to the surface. And we consider 2D materials, yes? So, and then if there is a, so this term is the signature of spin-orbit coupling. But then if we apply magnetic field, we make, for example, spin-down state energetically more favorable. What does it mean if you look on the Hamiltonian term? So it means that due to this term is called spin momentum locking, because spin is locked to momentum. Due to this, it will result in the fact that some momentum will be more favorable, yes, also as well. And this will lead to the appearance of the spontaneous current. But of course, the system will develop a phase gradient which exactly compensates this current. So this is, will result in the Fison homogeneous zero current state. The Q0 vector will be chosen in such a way to compensate these spontaneous currents, and this is called a helical state. So helical state is a rather recent topic. So for example, one of the first papers in 2005 in PRL was helical vortex fuzz detected in non-center-symmetric superconductors. Then there was a theory of what's happening. I was trying not to. Okay, thank you very much. Then was a theory for quasi-classical theory for disordered Rashba superconductors, which means Rashba spin-orbit coupling in superconductors. And in our case, we consider so-called hybrid helical state. In a few minutes, I will tell what it is. So actually, my talk is based on the single paper. It still did not published. It's submitted to PhysRevB, and one of the main workers is my PhD student, Erjan Karabasov, also collaborating Irina Babkova and Alexander Golubov. Probably you already know them. And a few words first about topological insulator. So this is, I show this slide in many other talks. So what is important that it's, we will consider 3D topological insulator, because there exists 2D, of course, also. That means that the bulk is insulating, the surface is a conductor, and it's not just a conductor, it's conductor with this spin orbit, strong spin orbit coupling and spin momentum locking. So spins are locked to momentum on this Dirac cone. What will be our system? Why I call it hybrid helical state? Because in our case there is no, there is a spatial separation of ferromagnetic order and of superconducting order. And still we have a helical state. So what we will consider? We consider a three-dimensional topological insulator. On top of it, on its conducting surface, we have a hybrid structure considered of ferromagnetic insulator or ferromagnet with superconductor. So we consider what is happening on the conducting surface of topological insulator, and we will roughly divide it in two parts. One part is topological surface with induced ferromagnetic order, another with induced superconducting order due to superconducting proximity effect. So then it's, that's why we call it hybrid helical state. And of course, due to this three ingredients altogether, ferromagnetic order, spin-orbit coupling, and topological insulator, will, which produce spin-orbit coupling, we have a helical state, and then of course we have spontaneous currents distributed over the system. And what I should also say, the system is finite in x direction, but infinite in y direction. So I briefly say a few words about model. So model, we start with Uzadal equations, which are valid in dirty limit. And in case when we calculate a critical temperature, we linearize them. So these are linearized Uzadal equation in superconductor, gap equation, and so-called Uzadal equation in topological insulator, which was derived actually in this paper of Zuzan, Mohammed Ali Dost, and Daniel Loss in 2016. And what I also should say, after calculations, we mentioned that so exchange field, H, is a field of ferromagnetic insulator or ferromagnet. It can have, because we have two-dimensional system, two HY and HX, and HY is not important for us. It just enters as a phase factor and did not come to any physical variable. But HX component has an impact on the critical temperature, for example, and on diode effect and so on. So we just call it H in the end. So then we have the following NZs, which actually reflects the situations that we have this helical state. And the problem is to find this Q. Q, it depends on the state of the system. So, of course, Kupriyanov-Lukachev boundary conditions. On the boundary condition between ferromagnetic insulator and superconductor, we have two parameters. One, basically, is the strength of inverse proximity effect. So sigma is a conductance, and Xn is a coherence length in both materials. And another is the strength of the interface barrier. So if we have a large gamma B, then we have a large strong insulating barrier here. And when it comes to supercurrent calculation, we actually use non-linear Uzadel equation. So first, hybrid helical state, and here I proceed to the results. So we calculate critical temperature for two directions of the exchange field. So you see the critical temperature has different values. And what is interesting that the maximum of TC don't correspond to zero momentum Q. So that exactly means that we have a helical state, because in principle the system should choose the situation with the maximum of critical temperature. So actually either this or this, depending on the direction of the exchange field. And you see that it doesn't correspond to zero Q. So it does mean that there is a helical state, and if we so we call this point QS. QS is a ground state of the system with this Q. So if we plot this QS as a function of exchange field, alpha here is just Fermi velocity, it's just to normalize. We see that this plot actually drops, means coming to the normal state, and nature naturally, if we have transparent barrier, gamma B is equal, it means transparent barrier between ferromagnet and superconductor. Then this Q is most pronounced because we need this ingredient exchange field to develop the helical state. So here I have some analytical results for actually very small Q, where thickness small and gamma B is 0. I just show it's quite interesting that this result is proportional to this factor. Later I will get this factor in analytical result of other sense, of analytical result for the diode effect. And it means I will comment it later. So here I just prove that QS is a node function of H. And let's go further. So we also calculate supercurrent. You see supercurrent is distributed. So there is a density of current. And to calculate, it flows only in the x direction because, I'm sorry, in the y direction. Because it's the direction where we have the oscillations of the exponential, this phase factor of the delta potential. And we should integrate on both F layer and S layer to calculate the whole current. So this I will call IT and this IS. IT means ferromagnetic part, IS superconductor part. So if we see the plot, this is the supercurrent, we immediately see that there is a non-reciprocal behavior, so-called. You see, so this curve, so this minima exactly correspond to black maxima. Actually, these two curves are for two different direction of exchange field. So red curve is plus H, black curve is minus H. So you see that there is a difference in maxima and minima. It can see if we consider these two defects. So this is non-reciprocity. We also see that it's, you see, non-linearity. So this part is smaller than this. And this state is chosen if, you see, it again corresponds for non-zero Q, if we have no current in the system. If we applied external current to the system, the current, this state will choose different Q, of course, if we have some current bias. If we apply currents higher than this, it will mean that the system will immediately go to the normal state. What is also interesting that there is some, you see there are two Q corresponding to the same current. Actually, in calculation we have showed that smallest Q will be chosen because the temperature is larger, the critical temperature is larger for the smaller Q, which means that in these two, this one will be chosen. So, due to this current non-reciprocity, I also would like to say you the distribution of the currents over the system. So, please pay attention that the scales are very different, unfortunately. So, Terjan prepared it like this. So, you see here's -1 and here's close to 0. So, it doesn't mean that the same color on the different plots are the same current densities. But this current densities for three different states. For state B is most interesting. When there is no current bias, then the system is in the ground state. Yes, and these two states when maximum and minimum currents, which means that we bias our system with some external current. And because of this current non-reciprocity, there is a possibility to develop a superconducting diode effect. What is this? So it means that if we have this system and we bias it with the current in one direction and then in the same current in the opposite direction. Actually, it means that the currents will be different. So in this direction, you see the current is larger, than in this direction, yeah, because there is a difference. It's not so big anyway, but there is a difference. In the middle, when there is no current bias, we have Q equal to QS, that's the ground state, and these two currents calculated in ferromagnetic and superconducting part will be exactly opposite to each other. So they are flying equal and flying in the different direction. And because of this, we can develop superconducting. Oh, it's again happening. What's it? Maybe I should be like this. Should be more careful. So what is superconducting diode effect? It's if we have a current in one direction, there is a non-zero critical temperature, everything is good. But if the current is applied in the other direction, it can be already normal state. So this is just a very radical case. And actually, diode effect was first observed and very recently by Ando and co-authors in layered systems. So they really discovered this current non-reciprocity. And it was then later theoretically proven with these materials with broken time reversal and inversion symmetry. It's some helical superconductors by these guys and also diode and co-authors. But now there is a huge amount of these papers who on theoretical papers on superconducting diode effect. And also I should mention the paper from the group of Bouzdin in Bordeaux. So they have very similar setup as ours, but instead of topological insulators, they introduced here, it's theoretical paper, introduced a boundary between superconducting and ferromagnet, which spin orbit coupling in the boundary. So the boundary condition implies spin orbit coupling. So they also have some teeny diode effect. In our case, we can plot this, what is the diode effect. So it's maximum minus minimum critical kite divide on the plus of these guys. And of course, you see it's 10 to minus 2, so it's not very high amplitude of this diode effect, but we studied the dependence of the exchange field. We see some some maximum. So there is some exchange field where the diode effect can have maximum. And this is dependence of the gamma parameter, which means how strong the inverse proximity effect. Actually, it does not plot it here. If we increase gamma more, it's again decay. So there is some optimal gamma. And this is the dependence of the strength of the gamma B. It's the strength of the tunnel barrier. So you see if the tunnel barrier is very weak, around 0, so it means almost transparent barrier, and we have a huge exchange field. Here we don't have any curve because superconductivity is broken by the exchange field in this case. Yes. So also we plot dependence on the temperature. We also have some interesting nonlinear behavior with some maximum in temperature. And finally, we did some analytical result for thin S and F layers, and actually here and small q. So this is valid. So this red curve is actually the numerical calculated curve, but black one is the analytical result. And what is interesting, so this result can be calculated in case of small exchange field, also small this factor, to the very interesting result. And this result we see, it's again, we can compare to result of QS. It's again governed by this factor, HDF over DS. So this is kind of factor which in case of small thicknesses, govern our superconducting diode effect. We also see here interesting dependence of the temperature. So then I'm coming to the end of my talk, and my review is that the ground state of the system is characterized by superconducting order parameter modulated with finite momentum Qs. So this state is accompanied by non-zero current distribution by zero average value. So, and this state is responsible for non-reciprocity of critical current, which actually manifests itself in superconducting diode effect. And also some important analytical results were derived. So again, thank you very much for your attention.
Okay, so the talk is open for questions.
You talked about the distribution current in X direction, but what about the distribution in Z direction? Does current flow in topological insulator surface?
Actually, in our model, we didn't consider it. In principle, in more sophisticated models, and it can be also considered, but in our model, we consider everything for simplicity just happening in 2D. Of course, if you have third dimension, in principle, it will be bad for the situation.
Thank you.
Thank you for your nice presentation. One question concerns this finite momentum. You are using an ansatz for the delta from the very beginning. And could you comment in more detail, how could you relate this momentum Q sub S to, for example, transport current or to other physical characteristics which are measurable? Thank you.
So in principle, we consider, yes, this ansatz, in principle, this immediately reflects this phase that we have this helical state, yes? So it's only with this ansatz we can, you would say why we choose this ansatz, no, why we don't use another one, yes?
No, this is good.
This is good, okay.
How to
Determine Q. Okay. Experimentally, you mean? So actually, I think there should be some indirect measurements with theory. So you, of course, you can measure this current non-reciprocity. For this is a measurable value. Then you immediately refer to the ground state Q. But there should be other. For example, you can measure critical temperature, yes? And so I would say that from this talk, the most correct way, the most easy way is to measure this current non-reciprocity. Then you immediately find the QS of your ground state.
A very naive question from an experimental point of view. You presented just planar structures, right?
Planar, yes.
Yeah, so there is some hope to see something of these effects in a simple, I don't know, bilayer structure in which the superconductor is in an intrinsic non-centrosymmetric superconductor.
This was already measured, yes.
The very first one that you showed?
This non-centrosymmetric layered superconductors, this was already measured there.
With a ferromagnet? Or?
No, not ferromagnet.
Okay.
Yeah, it's intrinsic and magnetic field.
Okay, in plane.
Yes, in plane,
okay.
Yes.
Thank you.
Any other question? Okay, if no,